So at the end of the chapter here, now we're going to be doing the most complicated probability concept. It's called conditional probability. Now, if you have dependent events, and you have two events, and the second one depends on the first one, then our product rule changes from just being probability of A times probability of B, that's when two things are independent, to probability of A times probability of B given that A has happened. So this little straight line there is telling you that something happened before. So we saw this in our one tree diagram in the last set, where you took two marbles out of the same bag. First, your probability of red was something like 5 out of 11. And then if you've taken a red one out, the second probability for red is now 4 out of 10, because there's one less in there, and there's only 4 left. And that's what this probability of B given A. So in that example, probability of getting that second red marble, given that one red marble was already taken out. So your total sample space went from 11 to 10, and the number of red marbles went from 5 to 4, if those were the numbers that were in that example. So creating our tree diagram, it's quite easy to see how those things happen, because you do one thing, and then you say, after that, what are my chances of getting the next event? Now, if we rearrange this formula, you can see we can get that probability of B given A all by itself by just dividing both sides by the probability of A. And this is a powerful formula because it can be used to figure out the chances of something happening in the past given something happening right now. And we'll look at a number of examples that have this. So conditional probability is when you're given a condition. And what it does is it reduces the size of the sample space, because you know some information. Sometimes conditional probability is really easy to see, especially if you have a Venn diagram or a chart to work with. So here we have 53 staff at school, 36 drink tea, 18 drink coffee, and 10 drink neither. So we can draw a Venn diagram to represent this whole thing. You'd probably start with a 10 on the outside, leaving 43 left in the other 3 circles. If you add the 36 plus the 18 up, that adds to 54. And since there's only supposed to be 43 in the middle section, you would say to yourself, I've added 11 too many. So that's how we could know that there's 11 in the middle. Or maybe you think there's supposed to be 43 left in the middle. I know that my entire green circle for the tea drinkers is 36. So in order to add up to 43, that means that this number here in black has to be 7, because 36 plus 7 makes the 43. And then you could figure out the rest of the values after that. So, simple probability. Person's chosen at random. Person drinks tea but not coffee. Well, out of the 53, what number would that be? The 25. That is not conditional probability. That is just a regular probability question. Part B is a conditional probability. You are told a condition. The person is a tea drinker. What is the chances they like coffee as well? So as soon as a condition is given, your sample space gets smaller. We're now not considering all 53 people. We are only considering the green circle, because they tell us it's a tea drinker. We can ignore these other 17 people. So what is the chances that person drinks coffee as well? There's going to be 11 out of those 36. So it's been reduced and gotten smaller. And when you're given a conditional probability question where you have a chart or a Venn diagram, like this one, it becomes obvious how the sample space has become smaller. It's pretty easy when they say it is a tea drinker that we're down to 36 people. And then the chances that the person likes coffee as well is 11 out of the 36. We could use the formula here to figure this out, and this is what the formula would look like. We want to find the probability of coffee given it's a tea drinker. So our formula says probability of coffee and tea. Well, out of the 53 people, that's 11 out of 53. Divided by the probability of getting a tea drinker. Well, there's 36 tea drinkers out of the 53. And you can see if you take that fraction, divide by the other fraction, and reduce it, you would get 11 out of 36 as well. Again, if he is a tea drinker, so you know that you're reduced to that circle out of 36. He does not drink coffee. Those would be the 25 out of the 36. So this first example is just getting us to see that what conditional probability does is it makes our sample space smaller. Because we're given a condition that means we can disregard other people. We know already it was a tea drinker, reduces our sample space from 53 down to 36. The second example here too is also quite intuitive. Find the probability that a card chosen at random from a deck of cards is the ace of spades, but you're told that the person got a black card. You're given that the card is black. What are your chances of getting the ace of spades? 1 out of 26. Again, intuitively, the condition that's given means we're now no longer thinking about all 52 cards. We were told it's black. That reduced our sample space down to 26. Now, how many of those 26 are the ace of spades? Only one of them. Here we could look at what does the formula look like. We want to find the probability of the ace of spades given it's black. What is the chances of getting the ace of spades and black? There's only one out of 52 cards that's the ace of spades and black. And the probability of getting a black card is 26 out of 52. Again, for these intuitive ones, you probably wouldn't go to the formula. You would just think about it and figure it out. This manufacturer has 3 different machines. You're producing some sort of goods. Machine 1 produces 40% of the cabinets, machine 2, 25%, machine 3, the other 35%. Machine 1 produces defective cabinets 8% of the time, machine 2, 15% of the time, and machine 3, 10% of the time. So chances are this business wants to produce a lot of materials. They've got 3 different machines. Machine 1 is the newest one, so they're using that one the most. And because it's newest, it's also the most efficient and doesn't make as many mistakes. But they can't keep up with all of the orders that they have just using machine 1, so they have to use some of their older machines as well. And sure enough, they're not as effective, especially machine 2 there, which 15% of the time makes something defective. But you still need to use it to fill all your orders. So a cabinet is randomly chosen and found to be defective. So now we take it off of the conveyor belt, open it up, it's defective. We can figure out all sorts of probabilities. For example, what is the probability it came from machine 3? So we know something in the present, and we can figure out the probability of something that happened in the past. This is what our tree diagram would look like. There's 2 events. First, a machine would be chosen, and then it either produces defective or not defective cabinets. And for questions like this where we don't have a Venn diagram or a chart to easily see what that condition reduces our sample space by, the formula becomes very nice to use. So our formula would look like this. We want to find the probability of machine 3 given it was defective. This formula is on your formula sheet, but I find this is one that I like to memorize. On the top of your fraction here, you're going to find the probability of both of those things together. So machine 3 and defective. That's going to be our 0.35 in machine 3 and 0.1 for defective. And on the bottom, when you're thinking about probability, is your sample space. Because we're given the condition that it's defective, that's our whole sample space. All of our defective ones is now our entire sample space. So that's why the probability of defective is on the bottom. So machine 3 and defective on the top, that's just 0.35 times by 0.1. Probability of getting something defective, can you see in your tree diagram that there's 3 different branches that will give a defective one, either through machine 1, machine 2, or machine 3? And you can type that entire thing into your calculator and get an answer. So I'd like you to try the formula for part B, and we'll put up the answer in a couple minutes. So putting things into the formula, machine 1 given not defective. So we do machine 1 and not defective over not defective, and you get approximately 0.411. If you change this back into an actual fraction with your calculator, I think it gives you 736 out of 1,791. This, I believe, is the answer from the first one, 33.5%. Now, another way that you can look at these conditional probability questions, if you want them, because this is not very intuitive to see how this answer works out, but if you wanted to, what you could do is you could pick a random number, a random big number. So I'm going to say, let's say we make 10,000 cabinets. And I'm trying to choose a number big enough so that when I do all my percentages, because machine 1 does 40%, machine 2 does 25%, machine 3 did 35%. So I could do these totals of 4,000, 2,500, and 3,500. And when I did 8% and 92%, 15% and 85%, 10% and 90%, I wanted to get ones that are all whole numbers. It wouldn't be wrong if you had decimals, but it's hard to think about 0.3 of a cabinet or something like that. So now I have all whole numbers. We have 10,000 in total. Of those 10,000 in total, 1,045 are defective, and 8,955 are fine. So in the first question, once I've created this chart, first question was, what is the probability it came from machine 3 given it was defective? If you're given that it's defective, you're not looking at all 10,000. You're only considering a new sample space of 1,045. How many from machine 3 were defective? 350. So if you would try 350 divided by 1,045, you would find out perfect. That's exactly 33.5%. This 736 out of 1791, I was given it's not defective. How many not defective are there? 8,955. How many of them come from machine 1? 3,680. And if you check that fraction, that's exactly the same as 41.1%. So there's another strategy that you can do for figuring out these ones. You randomly choose some large number and create your own chart of data. And once you have your own chart of data, then your condition, you can see how it will reduce your sample space. Given that it's defective, you're only looking at that 1,045. Given that it's not defective, you're looking at the other 8,955.